Hello everyone, welcome to this lecture in the Neural Network Coding from Scratch series. Today we are going to learn about three things. First thing is how to use numpy to code a neuron. Second thing is how to use numpy to code a layer of neurons. And third, how to use numpy to code a batch of data coming into a layer of neurons. So let's get started with this lecture. NumPy is one of the most popular packages for scientific computing in Python, and it's extensively used in neural network modeling. I've noticed that the reason a number of students struggle with understanding neural network dimensions and especially NumPy is because they fail to understand when one very fundamental mathematical operation, which is at the heart of everything related to neural network, and that is called as the dot product. A dot product will come up everywhere in neural networks. In the forward pass, you have to take a dot product multiple times when you multiply the weights with the inputs. And in the backward pass also, if you are to really understand the back propagation rule, you need to understand how a dot product works. Mathematically, I am going to show you how a dot product works, but I am also going to show you in NumPy what is the convention for taking a dot product. The reason this is confusing is that NumPy has the same command for taking a dot product between two vectors, a vector and a matrix, and also for the multiplication of two matrices. So for all of these three operations, you use a single command, and that is np.dot. This is the command which is to be used. Even when you're multiplying two matrices, even the same command has to be used. And this is where a lot of confusion arises from, because students get confused with the dimensions of what is entering into the dot operation. So let us understand this step by step. First, let us understand the dot product between two vectors. So let's say there is a vector A whose first element is A1, second element is A2, and third element is A3. And there is a vector B whose first element is B1, second element is B2, and third element is B3. When you take a dot product between these two vectors, what is essentially happening is the first element of A is multiplied with the first element of B. The second element of A is multiplied with the second element of B, and the third element of A is multiplied with the third element of B. And then all of these multiplications are added together. So when you do the dot product between two vectors in Python using the np.dot, the result is a1 b1 plus a2 b2 plus a3 b3. And you can scale it to as many number of elements in that particular vector. This is the first thing, and this is pretty easy to understand. The second thing, which is a bit more complex, is how do you take a dot product between a vector and a matrix. So let's say this is a vector A, which is 1, 2, and 3. And let's say this is a matrix B. Now, you can see that this is a 3 by 3 matrix. So I'm going to write the dimensions here 3 by 3. And this vector here has only one row and it has three columns. So this is 1 by 3. I want to now show you what does it mean when we say np.dot a comma b, and what does it mean when we say np.dot b comma a. So when I learnt dot product in mathematics, I only learnt about dot product between two vectors, and that's why it was very difficult for me to understand how can the same dot product operation be used between a vector and a matrix. The better way to think about it is in terms of matrix multiplication. So when you write the np.dot command between a vector and a matrix, or between a matrix and another matrix, think of it as Python trying to multiply the two matrices. So when I write np.dot a comma b, I first represent A as a matrix. So it's a 1 by 3 matrix. Remember that even a vector can be represented as a matrix. So A is a matrix with one row and three columns. and B is of course a matrix with 3 rows and 3 columns. So when you read np.dot a comma b, you can think of it as A matrix multiplied with B matrix. And remember the rule of matrix multiplication. The multiplication is only possible if the number of columns of the first matrix are the same as the number of rows of the second matrix. So here they are the same, so this multiplication will be possible. Okay. The way this works in words is that the first row, or in this case, since it's only a vector, this the row will be multiplied with the column of the matrix. So remember first of all that the output will have dimensions of 1 by 3. In matrix multiplication, if you are multiplying two matrices, the output dimension is always governed by the row of the first matrix and the columns, number of columns of the second matrix. So in this case, the output is going to be 1 by 3, because the rows of the first matrix are 1 and the number of columns of the second matrix are 3. So the output is going to be 1 by 3. Okay. Now, the first element of this output is the dot product between this vector and the first column. The second element of this output is the dot product between this vector and the second column. And the third element is the dot product between this vector and the third column. So the first element is np.dot a1, which is this full vector, and b1. So b1 is the column 4, 7, and 10. And we have already seen the dot product between two vectors here. So then the first element would be 1 multiplied by 4 plus, so then let me write it down over here. The first element would be 1 multiplied by 4 plus 2 multiplied by 7 plus 3 multiplied by 10, and this summation is 48. So the first element of the output is 48. Okay. Now let's look at the second element. The second element is np.dot a1 and b2, a1 and the second column. So then this will be 1 times 5 plus 2 times 8 plus 3 times 11, and this will be 54. The third element will be a1 multiplied by b3, or the dot product between a1 and the column b3. So then this will be 1 multiplied by 6 plus 2 multiplied by 9 plus 3 multiplied by 12. So then this will be 60. So then the answer is a vector which is 1 by 3, 58, 48, 54, and 60. Okay. So remember that when you take a dot product between a vector and a matrix, usually what happens is that the rows are multiplied by the columns. So the rows, which is a1, will be first multiplied or dot product with b1, then you will take the dot product between a1 and b2, then you will take the dot product between a1 and b3. So essentially there are three dot products being calculated. Now I want to ask you the question. Here I did np.dot a comma b, right? What would be the result of np.dot b comma a? So what if I reverse the order? So first of all, remember that Python treats these as matrix multiplications, right? So when you do this, first the matrix B will be written 3 by 3, but matrix, so first the matrix B will be written by Python, and this is, as I have mentioned over here, this is 3 by 3, but it cannot just write matrix A as a row vector 1, 2, 3, because if it writes it like this will have one row and 3 columns, and then these two matrices then cannot be multiplied because the columns of the first matrix are not equal to the rows of the second matrix. So then that's why then the second matrix has to be represented in the column format. So that's why it represents A in the column format, which is 3 by 1. Again, remember that the rule carries. The rows of the first matrix will be multiplied with the columns of the second matrix. So then if the rows are called B1, B2, and B3, and if this is called A1, now we take the dot product between B1 and A1. we take the dot product between B2 and A1, and we take the dot product between B3 and A1. Remember, this is very different than the previous case. In the previous case, we looked at the columns of this matrix because it came second. We looked at the columns of the B matrix, but now we are looking at the rows of the B matrix. Why? Because whatever comes first in this dot product, we consider its rows. Always remember this. This is the intuition which we need to keep in mind, right? When you take dot product of two quantities, the rows of the first quantity will be multiplied with the columns of the second quantity. Just keep that in mind. So then the rows are b1, b2, b3, and the column is a1. So first we take the dot product between b1 and a1, then we take the dot product between b2 and a1, and then we take the dot product between b3 and a1. So then this answer would be 4 plus 10 plus 18, which will be 32. Then the second would be 7 plus 16 plus 27, which is 50. And the third dot product between A1 and B3 will be 10 plus 22, which is 32 plus 36, which is 68. So remember that in this case, np.dot A comma B is not equal to np.dot B comma A. So you have to be very careful about which entity comes first and which entity comes second, especially when you are taking a dot product between a vector and a matrix. If you are multiplying, or if you are taking the dot product between a vector and a vector, then we can very confidently say that np.dot A comma B is equal to np.dot B comma A. But this is not the case when you take the dot product between a vector and a matrix. And when we look at layers of a neural network, you definitely need to keep this in mind. Not many students know about this distinction, and they think that they have understood the uh, math behind numpy layers. But unless you know this distinction, you will not be able to understand that math fully. Okay, so this is regarding the dot product between a vector and a matrix. Now let's look at the dot product between the matrix and a matrix. As I told you before, when we take the dot product between a matrix and a matrix, Python will treat it as a multiplication between two matrices. So, if this is the first A matrix, which is 3 by 4, and if this is the second, if this is a B matrix, which is 4 by 3, if you take np.dot A comma B, it will treat it as a matrix multiplication, matrix A multiplied by B. And can you check whether these matrices can be multiplied? Check the number of columns of the first matrix, which is 4. This is the same as the number of rows of the second matrix. So great, these matrices can be multiplied, and the resulting matrix would be the rows of the first matrix and the columns of the second matrix, which is 3 by 3. So this is the resultant matrix. The same rule which we saw previously holds here. Rows of the first matrix will be multiplied by the columns of the second matrix. So look at the resultant matrix. The first element of the resultant matrix is the dot product between the first row and the first column. The second element of the resultant matrix is the dot product between the first row and the second column. And the third element of the resultant matrix in the first row will be the dot product between this R1 and C3, which is the third column. So the way to visualize this is that, let's say you want to find the dot product between A and B, right? Or the multiplication. You want to fill in the first row. So if you want to fill in the first row of the resultant matrix, don't even look at the other two rows. Don't look at the other two rows of A1. Just look at this. First take the dot product of this with this. That will give you the first element of the first row. Then take the dot product of this row with the second column. This will give you the second element of the first row. Then take the dot product of this with the third column. That will give you the third element in the first row. Now when you want to look at the second row of the resultant matrix, what you can do is you can look at the second row of the first matrix and not look at any other rows. So then you can take the dot product of this with the first. That will give you the first element, then similarly second element and third element. And when you want to look at the third row, then you look at the third row of the first matrix, and you take its dot product with the first column, the second column, and the third column, and similarly you fill these three entries. That's how a dot product is done between two matrices. And if you want to multiply two matrices in Python, the command is np.dot a multiplied by b. But remember that for this multiplication to happen, the number of columns of the first matrix should be the same as the number of rows of the second matrix. Great. So now I hope you are comfortable with this np.dot command in Python, and using the same command, how we can take a dot product between vector and a vector, between vector and a matrix, and between matrix and a matrix. You will see that each of these three will be very important to us. Between vector and vector will be very important when we look at a neuron. The dot product between a vector and a matrix will be very important when we look at a layer, and the dot product between matrix and a matrix will be very important when we look at a batch of data. So make sure that you have really understood these concepts before proceeding with the next part of the lecture. Okay, now we are going to code using numpy in Python. First, we are going to code a single neuron. Okay, so let's say we have a neuron. Okay, so let's say we have a neuron with three inputs: x1, x2, x3. W1, W2, W3 are the weights, and B is the bias. We know that the output of this neuron has to be x1 w1 plus x2 w2 plus x3 w3 plus b, right? Based on your learnings of the dot product, can you think what this can be written as? If we construct a vector x, which is x1, x2, and x3, and if we construct a vector w, which is w1, w2, and w3, this thing can be written as np.dot x comma w, and then we can just add b. That's exactly what is done in the code. So instead of just writing everything explicitly, we can of course write x1 w1 plus x2 w2 plus x3 w3 plus b. But if there are 100 inputs, how can you write everything explicitly like this? That's when the dot product comes into the picture. So now to code the single neuron, we just write np.dot weights comma inputs plus bias. That's it. The inputs are represented as a list here, and the weights are also represented as a list. So in Python it is possible to take the dot product between two lists because then it treats them as vectors. So remember what we learned about dot product. um, if this is the inputs and these are the weights, when we take the dot product between weights and inputs, it just multiplies the first element of each vector and then adds it. So x1 will be multiplied by w1, x2 with w2, x3 with w3, x4 with w4. But don't forget to add a bias. So the output is the dot product between weights and inputs plus the bias. Remember that this same thing can also be written as dot product between inputs and the weights. And why can this same thing be written? Because from what we saw in our first section of this lecture, when we take a dot product of a vector and a vector, np.dot a comma b is the same as np.dot b comma a. So as you can see, we have written the code for the neuron output in Python, and it's much simplified using numpy. It is as simple as that to write this particular code. Now even if you have inputs to a huge number of inputs, and even if weights are also increased by a huge number, this same output command will hold. You don't have to write it explicitly every single time. And that is the advantage of using the dot product. It just makes coding very efficient and easy. Okay, so this is the way we code a single neuron in Python using numpy. Now let us look at a layer. So after we looked at neuron, we are going to now look at a layer. Okay, so we have a We have four inputs x1, x2, x3, x4, and we have three neurons 1, 2, and 3. So let me again go through to this. Look at this demonstration over here. We have four inputs and we have three neurons. From every neuron, there will be an output, and that will depend on the weights associated with each neuron. So let us look at the first neuron initially. It has four weights. From x1 it has weight w11, for x2 it has weight w12, for x3 it has weight w13, and for x4 it has weight w14, and the output is written as this. Now this can also be np.dot w1 comma x plus b1. Similarly, for the second neuron, the output can be written as np.dot w2 comma x plus b2. And similarly, for the third neuron, the output can be written as np.dot w3 comma x plus b3. So when we are looking at the output of the layers, we will have three outputs. We will have an output from the first neuron, we will have an output from the second neuron, and we will have an output from the third neuron. So the result will be a vector with three elements. The question is, how will you represent this in Python? You can either say that, um, you can say that my vector is this np.dot, this is my resultant vector w1 comma x plus b1. This is the first element of the vector. The second element is np.dot w2 comma x plus b2, and the third element is np.dot w3 comma x plus b3. You can code this out in Python, but again the problem is that if the number of inputs increase and if the number of neurons increase, will you write this for every single neuron? Imagine there are 50 neurons. How can you write this same wording for 50 neurons? Um, it will lead to a lot of manual effort, right? But then there is a trick. Remember when we looked at the dot product between a vector and a matrix? The resultant was three dot products like this. So what if these three dot products which we saw here, what if this can be written as the dot product between a vector and a matrix? What if it can be written like this? So in particular, let me try to motivate this further. So what if I write my W matrix, which is the weight matrix, as something like this: W11, W12, W13, W14, W21, W22, W23, W24, and W31, W32, W33, and W34. Now, if I write my weight matrix like this, the first row will be W1, the second row will be W2, which is the weights associated with the second neuron, third row will be W3, okay, and my X is my input, which is, let's say, X1, X2, X3, and X4. Now, what I invite you to consider is np.dot w comma x. What will this be? Look at what we have learned previously. This is exactly np.dot a comma b, which we have seen here. Or rather, it's np.dot b comma a, because the matrix comes first. Remember what we saw? The first row will be multiplied by the column, second row will be multiplied by column, and third row will be multiplied by column. So we'll have kind of like three dot products here, right? So similarly, if I do np.dot w comma x, remember the intuition I taught you, the first row will be multiplied by the column. So then this will be np.dot w1 comma x The second row will be multiplied by a column. So it will be np.dot w2 comma x, and the third row will be multiplied by the column. So then it will be np.dot w3 comma x. This is exactly what we wanted here. So now we don't have to write this explicitly. The output of the layer can just be expressed as np.dot w comma x plus b, where b is the collection of bias terms b1, b2, and b3. And what is the resultant dimension of this dot product? So this is 3 by 4 and this is 4 by 1. So then the resultant dimensions will take the rows of the first matrix and the columns of the second. So it will be 3 by 1. And the bias is also 3 by 1. So we can actually add these two vectors with each other. And that is exactly how the operations are done when we consider layers, right? Let's say these are the inputs, four inputs. This is my W1, this is my W2, and this is my W3. We are going to do np.dot weights and inputs. So this means we'll first take the dot product of the first row, which is W1, and the inputs. This is actually the output of the first neuron when we add bias to it. It's this output. Then what we are going to do, the second element of the resultant vector would be the dot product between W2 and the input. This will be the output of the second neuron. And the third element will be the dot product between the W3 and the inputs, which is the output of the third neuron. And then we just have to add a bias term to this. So then the layer output can just be written as a single term np.dot weights comma input plus bias. That's it. This is the advantage of the dot product. You can write even complicated outputs in a single representation like this. If you have really understood this, I want you to pause here and think about what if you mistakenly did this np.dot inputs comma weights plus b. So what if you accidentally did np.dot x comma w plus b? So what if you put inputs first in this dot product? So pause here and think about it. Okay, so let me tell you the answer. Remember, if you write this thing, I told you the rows will be rows of the first element will be multiplied by the columns of this, correct? Which means the inputs will be multiplied by the column, which means the inputs will be multiplied by these weight values, and that is meaningless because these weight values do not correspond to one neuron. What I've highlighted here is the first element of the three neurons. Instead, we need the horizontal, we need the rows because the rows correspond to weights of the each neuron. Instead, if you do np.dot inputs comma weights, you will get an answer which, so inputs is four rows and sorry, one row and four column, and then weights will be four rows and three columns. So you will get an output which is one row and three columns. Let me check that. So input np.dot inputs comma weights, right? So then inputs. So let me write inputs as 1, 2, 3, and 2.5, and then weights will be written as this weight matrix over here. So this is actually three rows and four columns. In fact, the problem here would be that it would be impossible to multiply directly np.dot inputs comma weights because the columns of the first matrix 4 do not align with the rows of the second matrix. So this would be impossible anyways. So you will need to take the transpose to get to the correct answer. But these are the considerations which you need to make when looking at the dot product, right? So now you realize that if you did np.dot inputs comma weights, it would probably give you an error because the dimensions are not matching. So then you might need to take the transpose of the weight matrix, and that might actually get you the correct answer. So check this for reference. So right now we did np.dot uh, w comma x, right? Check what you get with np.dot x comma w, and check what you get np.dot x comma w transpose. So check both of these things. My prediction is that if you do this, you might get the same answer as np.dot w comma x, but this will lead to an error. So this needs to be checked. But now I hope you are in a position where you understand the difference between changing the first element of a dot product and the second element and the implications it has. Secondly, now we have reached a stage where we understand that the output of a layer can be written just in terms of a dot product. So let's see how this is done in code. So now here are the layers of neurons using numpy coding. These are the four inputs. This is the weight matrix which has been written as a list of lists currently. Since we are taking a dot product between a vector and a matrix, this currently doesn't need to be converted into an array format. You can keep it as a list of lists. So the layer output is just the dot product between weights and input plus the biases. That's it. And then we print the layer output. If you did not use the dot product here, you would have to write the layer output as something like this. So you'll have to explicitly write down the output of every single neuron by multiplying the inputs and the weights and then adding the bias. And it just is a cumbersome process which takes a very long time. Even if you write this in the format of a loop, it still is a lot of code compared to the elegant way which we looked at here. In just one line, you can write the output of all the neurons in that particular layer. Okay, so after understanding how to code the layer using NumPy, we are now ready to look at a batch of data. So let me explain to you what this really means. Up till now, we have looked at single batch of inputs which are coming. So one batch is the input x1, x2, x3 and x4, and we have the output generated by every single neuron, correct? But what if there are multiple batches of data? So let's say there are three batches of data. In the first batch, the inputs are 1, 2, 3, and 2.5. In the second batch, 2, 5, -1, and 2.0. And in the third batch, we have -1.5, 2.7, 3.3, and -0.8. zero point 0.8. This can happen, right? Because usually there are multiple set of measurements which are done. Now, how will you represent the output of the layer? Remember that for each batch, these neurons will have an output, right? So the neurons will, for one batch there will be three outputs. For one batch there will be three outputs. For the second batch there will be three outputs, and for the third batch there will be three outputs. So the resultant is a 3 by 3 matrix. So how can we represent the output from a batch of data using matrix multiplication? So to understand this, first let's simply write down the batch of inputs in matrix format, and it looks like this. So each row of this, so the first row of this corresponds to the first batch. Let me call this B1. The second row of this corresponds to the second batch, which is B2. Third row of this corresponds to the third batch, which is B3. Correct? And this is the weight matrix. So this, the first row is W1, which is the weights of the first neuron. Second matrix is W2, which is the weights of the second neuron. And third matrix is W3, which is the weights of the third neuron. Now, what we want to do is that first let's focus on only the first batch, which means only the first row. I want to multiply this with the first neuron, so the weights of the first neuron. So I want to take a dot product between B1 and W1. That will give me the output of the first neuron for the first batch. So I want this. I want to take a dot product of B1 and W1. Then I want to take a dot product of B1 and W2. And then I want to take a dot product of B1 and B3. So I'm currently just looking at the first batch. This will be the output of the first neuron. This will be the output of the second neuron, and this will be the output of the third neuron. And as I look at the second batch, I want to take the dot product of B2, which is the second row, B2 with W1, B2 with W2, B2 with W3. And for the third batch, which is the third row, I want to take the dot product of B3 with W1, B3 with W2, and B3 with W3. This is my final answer, which I want. And if you look at it closely, it looks exactly like matrix multiplication, right? Look at what we saw in matrix multiplication, R1.C1, R1.C2, R1.C3. What we have written here looks exactly similar, B1.W1, B1.W2, B1.W3. In fact, it is just the multiplication of this matrix with the transpose of this matrix. If you directly multiply these two matrices, they won't multiply because the dimensions of X are 3 by 4 and the dimensions of W are 3 by 4. So the columns of the first matrix do not align with the rows. But if we take the transpose of this, so if we take the transpose of this, the column will be zero point 0.2, zero point 0.8, minus zero point 0.5 and 1. So now the column will be W1. And then if you take the dot product between this X and this is weights transpose, the first row will be multiplied by the first column. So B1 will be multiplied by W1, the second row B2 will be multiplied by W2, and the third row will be multiplied by W3. So what we want here right now is just the dot product between X and W transpose, or np.dot X and weight transpose. That's it. So even if you have a batch of data coming into a layer, you can represent it very nicely in the dot product format. So I have written it here again for reference. So the first row of this output is the first batch output for 3 neurons. The second row is the second batch output for 3 neurons. And the third row is the third batch output for the 3 neurons. And this is np.dot x comma transpose of w. Now, if you go to the coding interface, when we look at a batch of data, we looked at this figure already in the whiteboard, and we saw that we need to take a transpose of the weight matrix, which is very important. So if you can see here, we first have an input, and now we have three sets of input. This is the batch 1, this is the batch 2, and this is the batch 3. The weights are again what we mentioned earlier. These are the weights of the first neuron, these are the weights of the second neuron, and these are the weights of the third neuron. So if you look at this command, we take a dot product between the inputs and weights dot t, which is we take the transpose of the weight matrix as we discussed over here. It's very important to take the transpose. But you must notice that we added an np dot array, and the reason is because we cannot take transpose of lists in Python, and weights currently is written as a list of lists. So we need to first convert it into an array format, and then we need to take a transpose of this. That's why this particular command exists, np.array weights and then transpose. And then finally, don't forget to add the bias. So now you can hopefully start to appreciate the beauty of the dot product. We have looked at three different things today. We have looked at coding a single neuron using numpy. For that, only one line of output code has to be written. Then we looked at coding a layer of neurons using numpy. For that also, only one line of output needs to be written. Then we looked at coding a batch of data coming into a layer. Even for that, one line of output is sufficient. This is usually the kind of efficiency which is brought in when you start understanding matrices and linear algebra. If you don't study matrices, then it will be very hard because then you will have to write down every single thing from scratch. You cannot do it. You can write down every single thing from scratch when you learn neural networks like this. But it's just much more efficient to learn about matrices because as we go to the next chapters, which are activation functions, uh, things get a bit more complex since we add a number of layers to each other, and it's very important for you to understand matrix multiplication and matrix computations. For that, it was very important for you to understand the dot product and the role it plays in neuron coding, layer coding, and batch coding. So thank you so much, everyone. I hope you understood a lot of detail in this lecture. I'll be going into similar such detail in every lecture henceforth. So thank you, everyone, and I look forward to seeing you in the next lecture.